Good morning, all. My name is Kiran Chand, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today we are going to study half-wave rectifier. So let us see the overview of the today's session. So we are going to see again what is rectifier and different types of rectifiers, and we are going to study in detail about half-wave rectifier and what is the transformer used in half-wave rectifier and performance parameters of half-wave rectifier, and conclude with the summary. So what is rectifier? In the previous session we have discussed. So normal household power is AC. So AC means 230 volts AC at the power socket, and this is represented sinusoidal wave, and this 230 volts, but batteries provide DC. So DC means, so this is DC. So direct current, and there is no fluctuation. And what is rectification? Rectification means the device which converts AC into DC. So all power supplies need this DC because all electronic devices works under DC conditions only. So low resistance to the current in one direction, but high resistance to the current in the opposite direction. Okay. So if you see this is the block diagram of rectifier. So for this rectifier circuit, so we are giving 230 volts AC input and 50 hertz. Okay. And then this is your rectified output. So this rectified output means what? So here it is showing pulsating DC. This is called pulsating DC. Okay. So that is about overview of the rectifier. What rectifier means? It converts AC to DC. So which is required for the supply for the electronic gadgets. So what are the types of rectifiers we have? So rectifiers can be converted into two types. One is half-wave rectifier. So simply we write a HWR. Full wave rectifier. So simply we write full wave rectifier. But so the full wave rectifier is again divided into two types depending upon the transformer utilization. So here center tapped full wave rectifier and full wave bridge rectifier. So both are full wave rectifiers. So what is the basic difference between half wave rectifier and full wave rectifier means? So in half wave rectifier, the input signal, this is the input signal. In this only positive half cycle is utilized for the rectification purpose in half wave rectifier. Whereas in this full wave rectifier, so we use both positive half cycles for the rectification purpose. So that is the basic difference between half wave rectifier and full wave rectifier. Now let us see the half wave rectifier. So it is a simple and made with a single diode. So this is the another contrast, another difference between full wave rectifier and half wave rectifier. Half wave rectifier uses only single diode, and it is also utilize only one half of the input signal. So this is the circuit diagram. So here we have one transformer, and here we have a diode, one diode and one load resistor. Okay. So in this case, so this is the input signal. This input signal, AC input signal, is applied to the transformer. So here we have different kinds of transformer, which will be explained in the next slide. So to this transformer we are giving AC input, that is 230 volts, positive cycle and minus cycle and negative cycle. And here this is your result of output waveform, that is pulsating DC. This is pulsating DC, and again we have to require some more methods or some more circuit to convert this pulsating DC into pure DC using filters and then voltage regulator. This we have discussed in the starting class. Okay. So let us see what are the transformers used. So here the transformer, here transformer means transfers energy from primary to secondary coil. So primary coil means, so if you observe in the previous, so this is the transformer coil. Okay, this is primary coil and this is secondary coil. Okay, so therefore, see, transfers energy from, so 230 volts will be transferred to this, and depending upon this turns ratio, so these are the number of turns of the coil, primary coil and secondary coil. Depending upon the turns ratio, the 230 volts will be reduced to some low voltage. So here, what are the types of transformers? We have a step-up transformer, step-down transformer, and center tap transformer. So step-down transformer means 230 volts will be reduced to some 10 volts like that. So again, so here this is your 230 volts, and here you will have 10 volts, and this 10 volts will be given to your diode, and here you will have RL. And voltage transformation ratio of the this transformer is V2. So let us say the number of turns is N1 and here N2, and voltage across this coil is V1 and voltage across this coil is V2. So then voltage transformation ratio is given by V2 by V1 is equal to N2 by N1. So V2 means voltage across this secondary coil and V1 is the voltage across the primary coil. So the average value of half wave rectifier output voltage is Vm by pi, Vp. Vp means peak voltage. Peak to peak voltage, Vp by Vm. And effect of barrier potential. So we have a diode here. So it has got a barrier potential or cut-in voltage, and that is given by V out is equal to whatever the input voltage V in minus 0.7 volts. And now see the performance of parameters of a half wave rectifier. So there are almost 12 factors are there, parameters are there. This performance parameters judge the performance of a half wave rectifier. So average DC load current, DC load voltage, RMS current, DC output power, AC input power, efficiency, and then ripple factor, peak inverse voltage, PIV, transformer utilization factor, TUF, voltage regulation, form factor, and peak factor. Okay, so let us see one by one. Average DC load current, so that is represented with IDC. So mathematically the current waveform can be described as IL is equal to Im sin omega t. So we know the input signal is represented with a sinusoidal AC signal. Okay, so IL is equals to Im sin omega t. See here, Im means maximum peak value Im. So this IL is equal to Im sin omega t is holds good when your signal is in between 0 to pi. So that means this is 0 to pi and this is 2 pi. Okay, so from this 0 to pi, your Im is equals to your IL or load current is equal to Im sin omega t. So this is omega t. Okay, so sin omega t, because why? The output of the half wave rectifier is this one. Okay, so during negative half cycle, the diode does not conduct. So the diode is reverse biased during negative half cycle of the input signal. So therefore, we can represent the current through the diode is represented with 0 to pi, it is Im sin omega t, and pi to 2 pi, it is 0. So hence we have represent like this. So therefore, IDC is equal to, can be calculated with this formula 1 by 2 pi, 0 to 2 pi, IL sin IL d omega t, that is equals to 1 by 2 pi integral 0 to, see here, IDC means what? I average value of the load current. So that is given by, so if you integrate this 0 to 2 pi, so if you integrate this load current with 0 to pi, 2 pi, so in which only we consider half part, because during pi to 2 pi it is 0. So therefore we consider only 0 to pi. So Generally, when you want to calculate the average value, we have to integrate this from 0 to pi, 2 pi with the current value, and we have to divide this total value, that is time period 2 pi. So therefore 1 upon 2 pi 0 to 2 pi IL d omega t. So 1 by 2 pi 0 to 2 pi IL means we have given Im sin omega t and d omega t. And therefore IDC is equal to 1 by 2 pi 0 to 2 pi Im sin omega t. So Im by 2 pi, let it be taken into outside, Im by 2 pi. So integral sin omega t is minus cos omega t, and minus Im by 2 pi minus cos pi minus cos 0. So if you apply limits, so we consider only 0 to pi. So if you apply limit, minus cos 0 is minus 1, minus cos 0 is 1. So minus 2. So minus into minus plus. So this 2 gets cancelled, and therefore finally IDC or I average will be Im by pi. So this way you have to calculate the average DC load current. Similar to this, average DC load voltage can be calculated directly. So we know what is voltage. V is equal to I into R, that is according to Ohm's law. So what is I here? Because we are calculating DC, so therefore IDC into RL. So Im by pi into RL. So Im into RL by pi, or Im into R means what? Again Vm. So Vm by pi. Vm means what? Peak voltage. This is Vm. Similarly, note here Im is equal to Vm by. So we have to consider source resistance, the secondary winding resistance and forward resistance of the diode and load resistor. So if you consider all these resistance, then Im can be written as Vm by Rs plus Rf plus RL. Similarly, third parameter is RMS load current, IRMS. So in order to calculate this, we have to first squaring, finding mean and applying square root. So this is the procedure to calculate the RMS value of a particular parameter. So IRMS is equal to, so first the squaring of the given term, this is 1 by 2 pi. So 0 to 2 pi, 1 by 2 pi m sin omega t whole square d omega t under root. So Im can be taken outside because it is Im square. This is Im square, no? So therefore I can take it outside. So under root 1 by 2 pi. So what is the value of this? This is 1 by 1 minus integral sin omega t here, 1 minus cos 2 omega, because it is sin square omega t. So sin square omega t means 1 minus cos 2 omega t can be written as like this, 1 by 2. So therefore Im root of 1 by 2 pi, this is cos omega t by 2 sin minus sin omega t, 1 by, this means omega t, because in place of 1 I have this. Okay, so therefore 1 by 2 pi I can write like this, and sin omega t by 4 into d omega t. So finally you will get Im into 2 pi, then it is given by Im by 2, Vm by 2. So I got root of Im by 4 pi. So this is Im is there, and this is 1 by 4 pi. So under root means 1 by pi square you will get. So on top you will get pi. So pi gets cancelled. So finally you will get Im by 2. So therefore we can write IRMS value as Im by 2, peak current or maximum current upon 2. Similarly, we can also calculate the RMS load voltage, that is VRMS, directly can be written as Vm by 2. Next parameter is DC output power. So PDC, we know what is the formula for PDC is equal to V into I. P power is equal to Vi, or you can also write V is equal to IR, I into I, that's I square R. So different ways we can write. So here PDC means IDC square. In place of I can write IDC square and R place RL. So PDC is equal to IM square by pi square, because IDC, what is IDC? IDC is equal to IM by pi. So in place of IDC, I can write this is IM by IM square by pi square into RL, where IM is equal to VM, RS plus RF plus RL. What is RS? Secondary coil resistance, forward resistance of the diode, load resistance. So this is the expression for DC or average output power. AC input power, next parameter, PAC. So PAC means I square R, same formula, but here we are talking about AC. So IRMS square into RS plus RF plus RL. So therefore, I can write what is IRMS? Just now we have calculated IRMS is equal to IM by 2. So here IRMS square, so IM square by 4 into RS plus RF plus RL. So this is the formula for the AC input power. Similarly, efficiency. So what is efficiency? Eta is equal to DC output power by AC input power. So that is, what is this? We can, if you substitute all these values, this value and this value, so we will get 4 by pi square. 4 by pi square means what? 0.4052. So in percentage we can say 40.52. So efficiency of half wave rectifier is 40.52. So in about 100% only you get 40% power utilized. So remaining 60% power is wasted in the form of heat. So this is the drawback of your half wave rectifier. So next parameter is ripple factor. So ripple factor is defined as ratio of RMS value of AC component by DC value of component. Because this ripple factor is used to check whether your rectified output has got some ripples or AC component. Ripple means unwanted AC component. Okay. So for that purpose, we can check, measure the value of this ripple factor using this formula. So VR RMS by VDC. VR RMS means RMS value of AC component. So here VR RMS is given by this one, VRMS square minus VDC square. What is VRMS? VRMS means VM by 2, just now we have seen. And what about VDC? VDC means VM by pi. So therefore, we can write directly. So if you divide with VDC, we can write a root of VRMS square by VDC minus 1. So this is the expression for ripple factor. So RMS voltage. So just now we have discussed VRMS. VRMS value can be calculated using this. So how? 1 by 2 pi 0 to pi Vm square sin square omega t dt under root upon root. So if you do this, so you will get Vm by 2. So this is, we have done this RMS voltage, RMS current. So same procedure we have applied here. RMS voltage, VRMS can be written as Vm by 2. And therefore, if you substitute these values, so we find the ripple factor is about 1.21. That means in the half wave rectifier or the output of the half wave rectifier, that is rectified output of the half wave rectifier has 1.21%. So 121%. If you take the percentage of this, so you will have 121% ripples present in the half wave rectifier. This is also another drawback of half wave rectifier. And next one parameter, performance parameters of half wave rectifier is peak inverse voltage, PIV. So a diode can withstand maximum reverse voltage without disturbing or destroying the junction, PN junction. So that is called peak inverse voltage. So what is the peak inverse voltage? It can withstand, even you increase the up to what extent you can increase reverse voltage and your diode does not blast, or you can say without destroying the junction. So sometimes if you increase the reverse bias voltage, so obviously reverse voltage, the junction may break down, takes place. So therefore, it is the peak of the negative half cycle. So negative half cycle means this one, Vm. So this is the peak inverse voltage. So up to how much maximum voltage we can apply so that your diode does not destroy the junction. And next parameter is transformer utilization factor, and it is given by DC power delivered to the load and AC rating of the transformer secondary. So DC power delivered to the load means, so after this is the load RL. So here what is the power? So the power delivered to the load and power AC rating of this is the AC rating of the transformer secondary. Secondary means here. So that is given by PDC by PAC rated. So in the half wave rectifier circuit, the rated voltage of the transformer secondary is Vm by root 2. This is fixed. The secondary AC rating of the transformer secondary is Vm by root 2 because it is the AC signal. So but the actual RMS current flowing through the winding is only Im by 2, not Im by root 2. So please consider this. So therefore, if you substitute all these values, the transformer utilization factor TUF is given by 0.287. So if you take the percentage, so 28%, 28.7. So 28% only your transformer utilized properly for the rectification process. So another one is 10th is form factor. So it is another performance parameters of a half wave rectifier, and this is given by RMS value by average value. So if you substitute the value, so what is RMS value? Vm by 2, and what is average value? Vm by pi. So if you cancel this, you will get a pi by 2, that means 1.57 form factor. Similarly, peak factor, it is peak value of the rectified output by RMS value. So what is the peak value? Vm and Vm by 2. So you will get peak factor is 2. Okay. So these are the different performance parameters of a half wave rectifier. Okay. So let us see the summary. So what we have discussed today. So we have discussed what is rectifier and what are the different types of rectifiers. So we have half wave rectifier, full wave rectifier, and it is again divided into center tapped and bridge rectifier. Okay. And we have in detail we have discussed the operation of half wave rectifier and transformer used in the half wave rectifier and performance parameters of the half wave rectifier. Okay. So in the next class we will see the numerical problems on this half wave rectifier circuit. Thank you.